Rod and rails. A conducting rod, over here, of mass M can slide without friction on the top of two parallel rails connected to a resistor R. A uniform magnetic field B is oriented perpendicular to the plane of the rails. It's the X's here. At time equals 0, the rod is pushed to the right at an initial speed of V0. A. What is the direction of the induced current in the rod? Explain. B. Determine the induced current in the resistor at time t equals 0. And C. Determine direction and magnitude of the magnetic force on the rod at time t equals 0. What is the direction of the induced current? According to Lenz's law, an EMF and then a current will be induced in the loop to oppose the change in magnetic flux. So let's talk about the magnetic flux over here. As the rod is pushed to the right, the magnitude of the magnetic field remains constant. However, the flux through the loop, which is bounded by the rod and the rails, is increasing as the area, this area here, increases, right? Because as the rod goes here, then you have more area. So that's why the flux is increasing. So use the right-hand grip rule. That indicates the current will flow in the counterclockwise direction. And why is that? Well, it wants to oppose the increasing flux into the page, so it will generate a magnetic field out of the page. So if you put your thumb here, right-hand grip rule, it shows that over inside your loop, you'll have a magnetic field coming out of the page. So what kind of direction is this? This is counterclockwise. And again, you don't worry about the magnetic field out here, the induced magnetic field. You just worry about this one inside the loop. Determine the induced current in the resistor at time t equals 0. This is a handy-duty equation to memorize, okay? It was derived from either Faraday's law or balancing the forces on the rod. It's an equation you should memorize so you don't have to rederive it. But go ahead and look back in the notebook presentation to see the derivation because it's kind of cool. So the current, once you start pushing, is going to be EMF over R. Here's EMF. Make sure you put in V0 there. And this is going to be your current the moment you start pushing the rod. Find the direction and magnitude of the magnetic force on the rod at t equals 0. Well, we said the current was flowing counterclockwise, so through the rod, it's in the up direction as shown here. So you use magnetic forces IL cross B, and you can use the right-hand rule there. So you put your four fingers in the direction of the current, face your palm, and you're using your right hand, face your palm into the page because that's the magnetic field, the applied magnetic field, and your thumb should be pointing to the left. So that tells you that the magnetic force is to the left. It's resisting the push. Let's find the magnitude of the magnetic force. We were told that the magnetic field is perpendicular everywhere to the conventional current flow, right? Because the current flow is in the plane of the page, and the magnetic field is into the page. So the magnitude of the cross product over here is just going to be ILB. And now it's just a question of substituting in the current at time 0, which we've already found, multiplying some stuff out, and here's our answer. B squared L squared V0 over R.